thought I would talk a little bit about some of the technology that I've been involved in building and perhaps some of the things I have figured out along the way. I should say at the outset, I said when I was asked if I'd come and talk here, I said, I think this is a year or two too early, because we are, in a year or two, I think we will actually be dealing with genuine live petabytes and so on. Now, we're not yet dealing with petabytes. So I'll talk about a bunch of things that we're doing, but there are no petabytes involved yet. So the big thing that I've been involved in sort of pulling together, actually it's the result of about 30 years of progressive effort, is what we call the Wolfram language. This is sort of something that's emerged from a lot of work that we've done with Mathematica over the course of now 28 years, together with the work that we did with Wolfram Alpha and so on. Mathematica, something that I made originally because I was actually the second computer language that I built, was released in 1988, and it gets used at lots and lots of R&D places, most universities, and so on, to do all kinds of things. Wolfram Alpha is a much more consumer product that gets used by people to do natural language, computational knowledge queries, either on the web or through things like Siri and so on, and it's much more of a consumer thing. The Wolfram language is kind of a merger of those two things, and kind of the summation of what I've been trying to do. It's kind of it's just sort of emerging in this this last year, this year. It's kind of just emerging into the world. And kind of the idea of the Wolfram language is to do something a little different than pretty much any other language has tried to do, which is instead of saying, let's have a small core of functionality within the language, and then let's have everybody build on that core and maybe build libraries and so on that do particular things, the idea of the Wolfram language is to have as much as possible built into the language. I talk about it as a knowledge-based language, where as much knowledge about computation and about the world as possible is built right into the language. It's a lot more work on the part of the language designer to do that. It's kind of the story of the last 30 years of my life, trying to sort of keep coherent this process of designing a language that tries to incorporate all these different kinds of things. So, well, let me show you what I'm actually talking about here. So this is sort of a typical, these are things we call notebooks, which we invented 25 years ago now. Sort of the idea is, you type your computation here, you get a result, REPL type style in modern terms. This is not the only mechanism for interacting with the Wolfram language, but it's the one that people use a lot, both in doing exploratory work and also in programming. So what kinds of things? So sort of the idea of the language is to be able to handle all sorts of things. So let's say I want to make a random graph. Let's say I'll make a random graph, 100 nodes, 200 edges. So there it is. Maybe we can make it a bit bigger if we want to. But let's the idea, we can deal perfectly well with million node graphs and so on. Then we might say, let's make a plot, figure out the communities in this graph. There's the result. It's kind of nice to be able to just pick up the object that you have and stick it right in your piece of code here. We can deal with all kinds of different types of objects. So I don't know, we could, for example, let's pick up an image here. Okay, let's try again. There we go. There's a bad image, and we can now go and do whatever computation we want on that image. So we can, there's the image. We could take that image, and we could say, let's partition that image into little pieces, I don't know, size 20 pieces or something. Let's go ahead and do something. I don't know, what could we do here? We could maybe say map, let's say rotate through some angle, theta, for example, that each one of those little images, let's say map that there. Let's make that into something interactive. Oops. Let's manipulate this with theta going from 0 to 2 pi. Okay, so now what we should have here is a little interface which allows us to go and do funny things like that. Not this particular thing is not terribly useful, but that's a maybe I can let's go back here and take these. let's say, let's just sort each row here, and let's maybe assemble each of the sorted rows into an original picture, and maybe I can make that dynamic, and then I can take that out and just say, put a current image in here, and go. And now I've got something which will work in real time here. So, okay. So in any case, part of the idea is of the language is to be able to deal with lots of different kinds of data in a very uniform way. Part of the way that that's achieved is this is a fundamentally symbolic language. So, normally in most languages, if you type in X, it will say what's the value of X. Here, X is just X. If you want to treat X as something algebraic, you can go ahead and do that. If you want to treat any of these kinds of things as just another type of symbolic construct. And so, for example, there's a whole language that we started building 28 years ago now for dealing with symbolic things. It's sort of interesting when you have a symbolic language, both you get to represent any kind of data in a very uniform way, and also there are nice little features like that any fragment of a program is also a runnable thing. And that's very useful when you're actually building up code, because you can pick up a piece of a program and expect it to actually be something you can run. So we can go ahead and we can do whatever we want with in this case we're using some kind of typesetting construct. We could go ahead if we wanted to, I don't know, let's pick up we could I don't know, we could do something like this if we wanted to. All of these different pieces will just fit together in some convenient way. So the first kind of thing we've been trying to do is represent lots of different kinds of things in a uniform way symbolically. A big area that we're interested in is kind of things about this is all sort of abstract stuff, graphs and images and formulas and things like that. But what about things about sort of the real world? So for example, let's say we type in something like this. This is now just another kind of symbolic object, New York City. And we could, for example, say, what's the population of New York City? There we get the result. This New York City thing is just another symbolic object like everything else. So for example, if I say, something like planets, that will be a symbolic thing. I can say, what's the list of entities associated with that thing? There they are. Now these are, again, just symbolic things. I could say, let me get, for each of those planets, there's some standard image of those planets. Hopefully, wake up, computer. There we go. And we could, for example, say, we have lots of data about things in the world. That was %89, just means line 89. It's a really lousy way to program, but it's a good thing if you're just doing things interactively to just work like that. Then we can say, what's the mass of each of those planets? And now, for instance, I don't know, let's say we want to make a collage of images where we show each planet, in a size proportional to the mass. Let me see, where are the images? Line 90. So this will now make a little collage of images with the size of the image proportional to the mass of the planet. Now we have data about lots of different kinds of things in the world. We've collected for Wolfram Alpha. We've collected. It's now a few tens of terabytes of data that contain, which is all, and the important aspect of that data for us is it's all computable data. It's all data where we understand what everything about the data and about how to compute things from the data. So, for example, we might have satellite data from a real-time feed from NORAD or something that gives us orbital elements, but then we also have the computations to be able to compute where is each particular satellite at this time and so on. One of the things that's happened, in the Wolfram Alpha project, sort of the first step is just, in Wolfram Alpha, the kind of the idea is, if I say where is the ISS or something here, and we'll go to Wolfram Alpha and it'll go and hopefully work out the position of the ISS. The idea of Wolfram Alpha is you're typing natural language queries, and then we're going to the underlying computable data that we have, and also using all the methods and models and algorithms and so on that we have encoded that come from all different areas of science and engineering and other places. So in this particular, and one of the other things about Wolfram Alpha, which is sort of significant for many uses, is that what it tries to do is always to sort of generate an automated report about the answer to the question we asked. So rather than just saying, the answer to that question is 42 or something, it will attempt to give you a report that tells you, sort of contextualizes whatever results it's giving, and sort of tries to tell you the things that it thinks you will find interesting as an answer to that question. That's something that's been of importance, I think, both in the consumer uses of Wolfram Alpha and in the corporate uses of Wolfram Alpha, where Wolfram Alpha is used as a way to, there's a lot of custom Wolfram Alphas out there in the world now, built for large organizations and so on, which allow them to make queries about their own internal data and so on. So back over here. So we're this is notice, by the way. I mean, there are a lot of things that for me are kind of trivial, but might be of interest. Like, for instance, obviously these quantities here have units, and we understand how to deal with things like units and so on, which is kind of relevant if you have scientific type data. Let's say that we want to let's do something. Let's find out. So in our language, there's a notion of where's here. Okay, let's find out how reasonable this is. Let's say we do this. Let's just make. How about we do a 1 mile radius around the place that the GeoIP location of this computer is. So we should get. Okay, that looks fairly inaccurate to me. That must be where the ISP for this is. It's not. I know that's not where we are right now. However, we should. I'm sure if we. Okay. There's now we've got. So now we could say something like geographics of a geodisk around Stanford of let's say 3 mile radius, and now we should get a more locally relevant picture. Okay, so back to so kind of the idea here is to be able to incorporate all sorts of different kinds of things into our language, so that we already know about lots of different areas, whether we know about them. Whether we know about the raw data about the real world, or whether we know about algorithms and so on for doing computations. So I don't know. Let's try something more algorithmic. Let's say we want to. How about we do something like this? Let's say capital cities in Europe, for example. Let's see what happens there. Okay, so there are some European capitals. Let's say. Let's see what happens if I say. Let's just get the coordinates for each of those cities, and now let's say, for example, I might want to do, let's say, a traveling salesman tour. So let's see what happens if I try this. Okay, so that gives me that's now, because we have a built-in sort of state-of-the-art traveling salesman tour algorithm, we can easily work out the sequence of those things. So let's take that. Let's take that there. Now let's go back here, line 97, okay. And let's say we put those capitals in the order that corresponds to that, and let's say we make a geolist plot of those things with joining them up. Let's see whether this works. And what we should get here is a nice traveling salesman tour. Come on, wake up. There we go. So there's a traveling salesman tour of the capital cities in Europe, for example. Now, to me, it's significant that it's possible to do something like this. I wasn't actually sure this was going to work, but it should have worked, but you never know. It's significant that it's possible to do things like this kind of interactively without, I don't have to go and think, where am I going to find the coordinates of the cities? Where am I going to find a library that does, traveling salesman to a problem, things like this. Okay, well, so we've worked a lot on trying to encode all of these different kinds of data and algorithms and so on. The thing we find is that what we spend most of our time on these days is what one might call meta-algorithms, rather than just straight algorithms. It's usually the case when, if you take any particular area, that there are some fairly well-developed algorithms in that area, and maybe there are even libraries that exist that implement those algorithms. But the real question is, can we get full automation? Can we get to the point where if a person just feeds in a problem that they have, that the right algorithm will get applied and they'll get an answer in the right form, or do they have to be experts in that particular area to be able to deal with these things? It's sort of interesting for us. We've been, for the last many years, been building up this kind of huge collection of different, very automated algorithms. That's been important to us because when we have a new area that we're tackling, what's tended to happen these days is that sort of the best new algorithm is not an algorithm that can easily be built from the ground up. It's an algorithm which needs building blocks that come from different areas. So for example, you might say, okay, I'm going to do, numerical integrals or something. You might say, well, that's a numerical problem. I should use some sort of low-level numerical computation, language methods, et cetera, to do that. But actually, that will not give you what would be today's best algorithm for those kinds of things. Because today, the best way to do numerical integrals fast is to do things like algebraic preprocessing, to do all sorts of fancy combinatorics, to figure out things about integration methods. Maybe you do some computational geometry and so on. If you have those building blocks available in a form where they all fit together, then you can make a really fast, great algorithm. If you have to build everything kind of from the ground up, you can't do that. And this has been a great advantage to us and has allowed us to kind of really accelerate in terms of algorithm production. But as I was saying, one of the things that's important there is this sort of algorithm automation process of saying, let's not just pick, let's not just provide 100 different algorithms for doing something. Let's provide one meta-algorithm which will automatically figure out which particular algorithm to use to do a computation. So as an example of an area where we've ended up doing lots of work in that is machine learning, where these days there's a lot. You can, if you want to get machine learning done on your data set, you can hire a machine learning expert, and they will do various things with it. But one of our goals was to see how much we could automate of the process of doing machine learning kinds of things. So in the end, one ends up with just a function like classify that just takes a data set, takes a training set, and let's see whether there's an example here. Here's a trivial example here. This is just so this would be something where we're saying make a data set of pictures. And there's a very tiny data set, obviously, and pick them for day or night. And then what we'll get out is this classifier function. In this particular case, it happened to use logistic regression as the method. There, maybe we can pick a picture back here. Let's see what happens if I do something like this. Let's see if I feed that picture into this classifier. So that's on line 103. Okay, there's the picture. Okay, that's a nighttime picture. It thinks from that training set. So it's been interesting to see to what extent we can successfully automate this process of, and this is sort of a typical example of one of these meta-algorithm kinds of things. We did something recently. We made a little image identifier, well, not so little actually, image identifier that will take, let's pick a picture from, I don't know, let's try me, get a picture of an eagle. Okay, some random. Okay. All right, so let's see what happens if I ask to image identify this eagle. Okay, that's encouraging. So the point here, again, it's a very automated thing. I mean, this is trained on a few tens of millions of images using some fancy modern neural net technique, plus a few things that we invented recently. And the end result is that we have this function in our language that just does image identification. So another thing that we've been interested in doing is not only automating kind of what happens inside the language, but also automating the deployment process for the language. So, for example, one of the things we can do is to take, let's create a little user interface here. Let's say we make something let's do something very trivial. Let's say, okay, let's do something like this. Okay, so this will make a little trivial user interface here, wiggles around. One of the things we want to do is to automate it to the point where we can deploy that to the cloud. So let's say we just say cloud deploy of that. What we get is a cloud object here. And if I go to that URL, I should get, if it wakes up, come on, wake up. There we go, okay. I should get something which is now just something that lives on the web and is now going back to our cloud to actually get the computations done. So the idea is to be able to take anything we do here and be able to deploy it to the cloud. I should say that the whole language actually will run in the cloud. Let's see. This has been a very painful thing to actually get to work after you've built a whole elaborate interface here that supports all sorts of sophisticated documents and so on, and you built that for over the course of a couple of decades. Having the whole thing be effectively re-implemented in JavaScript is a very painful process. But it's one that is now almost done. We're able to, I could take one of these things here, whatever I want, and I can just do the same thing here as I could do on the desktop, but now it's just operating in a web browser. So I could also do things like I could say, for example, let's say I want to make a form on the web, make a simple web app. I could say something like, I seem to often use this example, but let's say I have something where I'm going to make a picture. This is something trivial and silly, but perhaps illustrates the point. I can make a picture of a cat, popular on the web, right? And I specify a form that I want to be deployed on the web, and that form has one field. The type of that field is a cat breed. Because we have all of our natural language understanding system, we can understand maybe 500 or 1,000 different types of things. Let me just show you how that works. So we have, the way it works in the language is we have the notion of an interpreter. And so an interpreter might say, a city, and then we say something like NYC here, and it takes a string, a natural language string, and a specification of what kind of thing it is, and it will then give this sort of canonical semantic entity as the thing to manipulate in the language. Okay, so now we have our field here. We can type in a type of cat, and we'll then go and go to the cloud and generate our picture of a cat. If we want to make this something that we can put inside another program, we can create an API based on this, and so now this is a standard web API, which we gave 0 arguments to, but let's give it an actual argument. Let's say breed equals Manx or something, and now it will do the same thing, just using that web API. We could take that web API specification, and we could say, give me embed code for, I don't know, let's say Java, for example, to call that API. And so now in this particular case, because there isn't a cat breed data type in Java, the code won't be all that interesting. But if there was a data type that could be converted from a native Java into something that can be sent to our cloud, then it will look a little bit more interesting. There's just a way of calling our cloud from inside a Java program. And actually, there are more elaborate ways to do this. This is essentially the same idea, allows you not just to call from a language into the cloud, but also to call a local version of our engine on your computer. and we've been doing a lot of things with embedded processors recently, and the idea is to be able to use the same language whether you're operating on a little tiny embedded processor or whether you're operating on a big parallel system in the cloud, for example. I might mention in terms of parallelism, one of the things, I mean, we've had for a long time is the ability to do a certain degree of parallelism in our language. So if I just start off and I say make a parallel table of things, let's say I make a parallel table of process IDs, which isn't very exciting, but at least it'll show you that it's running on different, it's running multiple processors. If you look very quickly, it'll probably, this laptop probably has 4 processors, 4 cores in it, so you'll probably see it start up, there we go, it started up 4 cores, and it then distributed this utterly trivial computation across those 4 cores. We've done a lot, for years actually, we've had some grid-based computation tools that allow one to distribute computation across a parallel network. We're actually going to, fairly soon, have a nice sort of consumerized version of this that allows you to go up to about 1,000-way parallelism sort of interactively from just within a Wolfram language session. So let's see, other kinds of things to mention. I think another thing that's of interest to us is dealing with various different kinds of sensors and devices and data coming in from those kinds of things. And so we had a project actually we started a couple of years ago to just curate what are all the different kinds of devices that are collecting data these days. There's 4,000 of them listed here. And we'd be interested in how do we connect all of these to our language. In the case where, so one of the mechanisms that we have recently is the thing we call our data drop. And the idea there is to have an easy way for all sorts of devices to just drop data into our cloud. Now, by your standards, the amounts of data being dropped are utterly chicken feed trivial, because this is typically things that the case that we're dealing with right now is things that are dropping data less than once a second. So this is not huge amounts of data that are being supplied. What's interesting is the convenience of being able to just have within the language. I can ask for my particular personal, rather messy probably collection of data bins. But the idea is that every data bin just has a UUID effectively, and we can then, so let's pick out a random. How about, I'm a big personal analytics enthusiast. Let's see, that's a weird one. SW skin temperature. Okay, so let's say I could go ahead and say I want a time series of that, and now what we'll get out here, this will be, in this case, just retrieving into memory here that data. I should mention that the way this data drop works, it's using our kind of data semantics layer so that it's turning, and this is outrageously slow. I wonder what's going on here. This is turning, when the data comes in, it's sort of automatically processed so that it is semantic, so to speak. Okay, that wasn't a very, so here we, for example, got, okay, let's see what happens if I say this. This doesn't look very interesting, but let's okay, that was really boring. But I could, for example, say what's the mean of let's try the mean of that there. So this is, oops, what happened here? There we go. So that's so I can take this time series object. Again, in our language, a time series is just another kind of symbolic object which I can manipulate. And so in this case, I'm just asking what's the mean of that time series. I might mention one thing that's sort of emerging in our world, which is, let me show you this. This is a sort of symbolic computation meets, that's not what I wanted, meets databases. So this is a thing we call a data set, which is kind of a symbolic interpretation, so to speak, of a hierarchical collection of data. So for example, here I could take this data set, let's call it planets, for example, And I could do things, I could do all kinds of computation on it. For example, let's try taking, say, all comma mass. So that will get me the masses of the planets. And I could say, for example, show me, a bar chart of that. Okay, Jupiter is much bigger. Show me, for example, go back to the planets and say, let's take a look at what the structure of the thing is. Say, let's look at the planets. Let's look at all the planets. Let's take their moons, and let's go ahead and just do that. Okay, so these will be associations that are collections of properties of the moons. I could then say select in here hash mass, let's say greater than mass of the moon. Okay, let's see what happens here. And then I want to do that. And now what should happen, if I got this right, I think I may have done something kind of stupid here, but this will be just asking to, I know what I did that was a bad idea here. Okay, let me do this slightly differently. Let's say I compute. Okay, so this should give me the mass of the moon. Okay, let's take that mass. It should figure out to compute that once, but I probably didn't. Okay, there we go. So now what I did was I got from this data set, I extracted those moons that have a mass greater than the mass of the Earth's moon. Okay, and I can go in and I could go and say, for example, what could I do here? I could, for example, say what's the radius of those moons, and now maybe I can make I could take that and make a pie chart from that, or do other kinds of computations from that. And so the idea for us is this is a convenient way to package kind of structured data, and the thing that we're doing is the sort of the 0th version of this is an in-memory kind of thing that will work up to a gigabyte or something of data. There is also file-backed, database-backed, distributed database-backed versions of this that are coming. And the idea is that one can have sort of a uniform interface to all these different kinds of things that operate within this data set construct. Well, okay, I think, let's see. It's actually, there are many different things that I could talk about kind of the automation of computation and so on, but I think maybe and about sort of our experiences in trying to build a system. I should say one thing actually about data sets and queries and so on. One of the things that we've noticed, and when we've tried to make a nice kind of symbolic query language, we think it's a pretty good query language, but ultimately for consumer querying of things, I think it will be too complicated. It's simpler than SQL, but it's more powerful than lots of other kinds of things, but it's still kind of complicated. And I think one of the things that we're working a bunch on is how do we use the natural language understanding stack that we built for Wolfram Alpha to be able to synthesize queries and so on here. And that's a fairly promising thing. I mean, you can use, if I say, something like this, say plot a cosine curve or something, this is now going to use natural language to synthesize code here that we can then go and, let's say, add a yellow background, let's say. Now, this will again synthesize code and go and do the operation. And so, kind of the idea is to do that type of thing with queries also. Well, I think it'll be much more fun if we have a discussion here. So I should probably I gave you some kind of introduction to the technology that we've been trying to build. I'd be interested in questions, comments, telling us what we should do, anything else. Please, who wants to start?
I'll start.
Yeah.
All right, Tim. So my name's Tim Frazier. I'm with the Giant Magellan Telescope.
I saw you demo live at the Palace of Fine Arts for Mathematica 3. This is the second time. Still glad to see you're going strong. My question is, when you ask questions like city, NYC, can you do things like, what is NYC? In other words, not tell the computer it's a city, but try to deduce from context or other questions that that's what's going on.
Yeah, I mean...
And how do you do that? Is it a database of, people asked what is NYC, the most likely result is city, or other things?
So a question, it turns out that human language is less ambiguous than you might think. I mean, when we started the Wolfram Alpha project, I thought that all the time we'd be dealing with, people would type things in and we wouldn't know what they were talking about, okay? It turns out that it is really not, and I thought we would have to know things about the user. Is this somebody who's interested in chemistry? Is this somebody who's done this? That turns out not to be necessary most of the time. It turns out there's the sort of a priori probability, if I type K0, for example, here, I thought this conference might have, okay, so if you're a particle physicist, what is K0? Well, there might be some other things that it could be, but it's probably a particle, because that's the most common kind of thing that's actually called K0. It's only 2 characters. It's enough. So, when it comes to so I think the basic answer is that it's easier than you might think. I mean, it's been a lot of work to curate, many tens of millions of entities and so on, and figure out what are they called, so to speak, by people. And there's no kind of there's no intrinsic database of what are all the cities, even in the US, for example, what are they actually called by people? You have to go look at Wikipedia, you have to look at the web and so on to know, New York City is also called the Big Apple or something. But that's something that it's a large but finite problem. I mean, I think one of the general things that we've discovered about data and so on is that, curation is actually a worthwhile thing, and it's scary, but not as scary as you might think. I mean, there's a lot of data in the world, but it is definitely finite. There are definite, domains, categories, and so on. And doing this curation, I mean, it's taken us, a decade and a half or so to understand really how to make a good pipeline for doing curation and how to use the data that we've already collected to assist in the curation of new kinds of domains. The really shocking thing to me is after you've done a couple of thousand domains, you would think the next domain would be necessarily easy, but it never is. There's always some extra little twiddle about some domain that there's some weird feature of the way that people in that domain refer to things or the way the data is structured and so on. But it certainly helps in terms of the QA of the next domain. It's certainly a lot easier after you have a few thousand.
Just one follow-on, if I may. Yeah. So how much data does one need to curate to achieve this level of intelligence? I mean, I think you were talking in terms of not petabytes yet, but...
Yeah, I mean, for the things that are named, okay, so for example, I mean, there are all these different, we've got, I don't know how many named entities now we have, maybe 100 million or something. And that doesn't get you all the people with individual names in the world, but it gets you all the cities, lots of different kinds of things. Of course, there are many things, might say, well, what's the ontology of all of this? What we've ended up doing is inventing a kind of algorithmic take on ontology, which is not quite the same thing as the sort of static RDF type ontologies that operate with just, here are a specific set of entities, here are their relationships. Because it turns out a lot of things we deal with, there are, for example, an infinite number of integers, and we have to deal with that. There are, planets that change their positions and so on. So we have to deal with that. There's no sort of static ontological relationship between these things. So we have kind of a different approach to ontology that we've developed for those kinds of purposes. In terms of how we, it's been interesting to us recently with machine learning and doing this image identification thing. You might have, last week we put up a site on the web which seems to have gotten lots of traffic, at least, that's called imageidentify.com. And what happened to it? Wow. No, slow. Interesting. Well, anyway, it's wow. That's really surprising and interesting. Maybe there's maybe some curious thing just happened in the world that caused this. But anyway, this is a thing that's built actually with a tiny number of lines of code, of Wolfram language code on the inside. And it's just a consumer site for doing image identification. I showed you the internal function that does that somewhere up here. What's interesting about that is that's a fairly large amount of data that we dealt with, fairly large number of images. It involved a fair amount of curation to make, but that's it's dealing with about 10,000 picturable nouns basically, which is a fair fraction of the common picturable nouns in any language. Now, I've been rather interested in this relationship. You talk about sort of curating things and named entities and so on. I've been interested in the question of when you use systems like the kind of neural net systems we're using for this, it is effectively discovering categories of things for which we don't have words in our language. That is, it knows, in the first few layers of the neural network, it's going to know there are these things that you can distinguish that are blobby things that look like this versus, things with weird serrated boundaries that look like that. There doesn't happen to be a word in any language that describes those things, but yet this is a distinction that is a useful distinction. It's a useful sort of symbolic distinction that can be made in doing computation. And so I've been sort of interested in this question about how do we go beyond the sort of the named by humans entities to the things that are distinctions that come out of the world that we live in, so to speak, because image identification is something which is very specific to the world we live in. I mean, if you were to have a differently constructed world, it's not a mathematical theoretical thing. It's a thing that relates to the particulars of the world with actual objects in it and so on. And so I've been sort of interested in this question about the growth of kind of AI-generated entities, symbolic entities, and how that relates to the whole use of language and so on. This is a long and different topic. Okay, yes?
Hi, Martin Henschel from Snowflake. Thank you for this demo. It's very impressive. And I may be asking a mean question here, but since we're in Silicon Valley, what's the target audience of this language?
Everybody who's trying to do something algorithmic.
Is it for students? Is it intended for journalists? Is it
no, it's intended for people. I mean, look, it's used right now by a fair fraction of the world's kind of high-end R&D folk. It's used in Mathematica by, like 90% of universities in the US have site licenses for Mathematica, and it's widely used there. What's that? Yes. And so the thing that what's happened. So we've had a lot of success for many years with sort of the precursors of this in the R&D sector. What we've been interested in more recently is how do we make this language more deployable so that you can use it to, I should have said, those things that I was deploying, you can also deploy mobile apps and so on, and you can even deploy stuff to the Apple Watch now. The idea is that if you have an algorithmic idea, this language is intended as the sort of fastest path to getting that algorithmic idea to become a real thing that can be used in a real product. And there are plenty of examples of companies and so on that make use of our technology stack. I mean, there are, in the finance sector for many years, there have been lots of companies that have built trading systems based on our technology stack. I'll show you one example that's kind of fun, local Silicon Valley example. Here, let's see. This is an example of a company that's using Wolfram language as the base for what they're doing. It's a lab in the cloud company where the idea is to automate what happens in a biology or chemistry lab, and the notion is that you give your experiment, you specify your experiment as a Wolfram language script, basically. Then you press go, hopefully having reviewed what's going to happen, and then sort of robots swing into action and actually perform the experiment physically and then dump the data back into our cloud and into our language. So that's an example of that's a fairly high-end example of a use of the language for a sequence of things, for being able to specify symbolically, using the symbolic structure of the language to specify, in this case, a sequence of operations to be done for a biology experiment, being able to manage the data. I mean, this particular company I thought it was really cute when I visited them, and their machines are actually labeled with Wolfram language, code basically. The physical machines are labeled that way, so it's really making use of our language all the way through. But the target, I mean, this is really an emerging thing that it's possible, given what we built into the language and the automation that we've built, it's just now becoming possible to really go from the algorithmic idea to the deployed app, product, whatever, quickly. And this is something, I mean, we've been working very hard to solve this problem of making the language more deployable. This is something that just as the months have been going by recently has been more and more a solved problem. And it's kind of exciting for me to see, I've been out here for a day or so visiting a zillion companies that are starting to use or want to use our language to build all kinds of interesting things. So I think there's going to be a kind of a little Cambrian explosion, actually, of sort of algorithmic, of companies that can take an algorithm and really make something real out of it easily, that's enabled by what we've tried to do with language. So that's really the target. Now, you ask about students. One of the other interesting features of the language is that because we've automated so much, it's possible, as has happened in a lot of other areas. I don't know, if you take video editing, for example, what the high-end professionals do and what the students can do has kind of converged because, they can all use Final Cut Pro or something like that. This is what I think is happening here with kind of this kind of computational programming. And one of the things that's been interesting to us is sort of the level of interest, even in the K-12 sector, in using this language as sort of a language for teaching computational thinking, because it's something where you can immediately be dealing with kind of real-world things and so on. So that's another kind of growing direction, but that's sort of separate from the direction of Silicon Valley startups, so to speak. It's a different branch of what we're trying to do. But I think it's made possible by the fact that by sort of the same thing, which is having a very automated language where a lot has been built into it. That's the idea. Yeah.
Hi, my name is Mohammed Kalali. I'm from Denmark Education. One of the concerns I have is that you work in an education field. This would make our life very hard to catch students plagiarizing. For example, if you give them a problem and they can all type it and get an answer, how can we actually evaluate students on learning things rather than just using computers?
Not a question I would have expected at this conference, but I can address this. It's kind of interesting because a large fraction of students who, for example, do math in a place like the US use Wolfram Alpha, okay? I think the number, it's about once every 3 weeks on average for a typical student who's doing any math beyond algebra now. So they all use Wolfram Alpha, and their teachers know that too. And we kind of hear I hear occasionally people saying, if you go to Wolfram Alpha and you type in, I don't know, you work out some, let's do, you do some integral or something like this, it'll give you the answer. And you can even go here and say, show me a step-by-step solution. We actually started charging for these step-by-step solutions, which has turned out to be a fairly good move. Many more people care about this than you would think. But anyway, there's a bizarre little arms race going on between, can the teacher recognize that it just came from Wolfram Alpha? Actually, the shocking thing that's going to happen this fall is it's going to be harder and harder to recognize that because there's going to be more diversity in the kinds of step-by-step solutions that are generated. What this is telling us, probably, is that we're not teaching quite the right things, because by the time it's that automated to get an answer, maybe, I, for example, haven't done an integral by hand in probably 35 years. It's, one of my kids was doing a calculus class. I'm saying, I didn't think humans still did this kind of stuff. But, what's interesting is that when you can do things automatically, you get to do many more things. You get to really have, what's happened with me with integrals, for example, is I think I have really good intuition. Given that you show me some integral to do, I have really good intuition about what kind of form the answer might be in and all kinds of other things about it. Can I actually trace through all the details to do it? No. Probably not. I haven't tried in a long time. But what's interesting is when you have access to something where there's this much automation, you get to both teach about more interesting and more real-world things and get to kind of build up intuition in a way that you couldn't if you had to sort of do every step by hand. So that's my, I mean, education, it's interesting, the amount of data, we have a problem generator, which, just to say one thing that's just kind of silly in a sense. When we do one of these integrals, the actual internal doing of this integral takes milliseconds and is done with kind of big industrial strength techniques that will just bash through any integral that you could seriously imagine doing, okay? So that's how we actually do it. That's how we get to the answer. Then there's a question of, well, how do we show the steps for a human? That's actually a lot more work. It helps to know the answer, but we have to have all these things that are basically a sequence of rules that show what a student might do to go from here to there. Then we say, well, let's actually generate problems for students to solve. We want to generate problems of a certain level of difficulty. So we have to sample a problem, then we have to go and we have to figure out not just what the answer is, but what were the steps that might be taken so that we get a question that's of the right level of difficulty. So actually, that process takes a huge amount of computer time, effectively, by relative to other things, a huge amount of computer time to figure out, what is a problem that we should feed to the human that will be of the right level of difficulty, that they can go through these steps to answer it, even though in a millisecond we could have actually answered this question. And there's something a little bit wrong, I think, with this picture in terms of what it is that it's worthwhile for the humans to do. But this is a different topic.
So
Yes?
I have 2 questions here.
You mentioned earlier that you can install the system at, let's say, a customer site and then use their data to build that up. Could you say a few words about how that works, how it's customized?
Yeah. So, well, there are 2 different sort of technology layers here. One is Wolfram Alpha. Wolfram Alpha was built as a very kind of black box consumer thing, where you're typing natural language in, you're getting a report out. What happened 5-6 years ago when Wolfram Alpha first came out is lots of calls from CIOs of companies and so on saying, we've got all this data. We'd love to have it be processed using Wolfram Alpha type techniques. So we've now done a whole lot of these projects for a whole lot of large organizations where we basically go in and do the same kind of curation work on their internal data, working with their internal databases, and connecting those to the kind of Wolfram Alpha mechanism of natural language understanding. And typically, the best value comes from cases where it's sort of a mashup between public data that we already have and sort of public linguistics that we already have together with their internal data. And we've done this across a large number of industries now. One of the things that is sort of an emerging direction is more productizing that, because those projects are all fairly large projects that involve a fair amount of services work and so on. And now that we've done a bunch of these, we can see a lot of patterns in what gets done. And so we're sort of working slowly towards having a more streamlined way to do this kind of thing. I think that in some of those cases, what we've done now with the Wolfram language, which is a much more, Wolfram Alpha, as I say, is more of a black box, very simple. You type in the question, you get back the answer. Wolfram language it's a much more flexible kind of thing, and I think there's a lot of more interesting things can be done with that. But it's been there are a lot of things that are out there being used in all sorts of organizations that seem to work very nicely for lots of different purposes. So it's interesting for us.
Hi, thank you for the really, really great demo. It seems like the language has a lot of automation built in, which is great for integrals and things. But if you're doing machine learning tasks, maybe you don't know why it's picking a certain model, or you want more control over what parameters it picks and things like that. So what's your philosophy about balancing automation versus keeping the human and what is being done?
So we provide lots of knobs and switches. And if you want to set the knobs and switches, you are encouraged to do so. I would say that we feel proud of ourselves when we can automatically set the knobs and switches better than basically any human can set them. And that happens more than you would think. In other words, if we've done a good job of making a meta algorithm, it is rare that a human can do a better job of doing things with the particular knobs and switches. But we try to provide access to all of the various knobs and switches. We've done that our machine learning stuff, I would say, is kind of halfway towards all of the knobs and switches being exposed. Actually, for example, in the neural net case, we will have a nice symbolic language that exposes the whole network structure and so on, so that you can modify that if you want to. Yeah, I mean, it's easy for us to expose the knobs and switches typically. It is our goal to have people not have to use them. I mean, a shocking fact that I discovered a few years ago is that, about defaults and so on. Defaults and automation is really important to practical usage, and people are surprisingly, they say we want knobs and switches and so on. They use them once or twice, and then they say, it's not worth it. I'm just going to use the defaults. I'm going to use the automatic thing. And if we did a decent job, that will work a very large fraction of the time. I've seen a bunch of cases, like one of my favorites is we had a particular orientation for 3D graphics that we picked right when Mathematica version 1 came out. And then I thought I'd go back and look, in like physics journals and things, there are endless 3D pictures made with Mathematica. And guess what? Like 99% of them are from this particular default viewpoint. Okay, which is, we picked it with some intelligence. There was some thought put into it, so to speak. But it's trivial to change the viewpoint for a 3D graphic. But yet, in practice, people essentially always use the default, which puts more pressure on the language designer or the system developer to actually get the default right. But that tends to be what happens.
So I have a question. So LSST will classify about 40 billion stars and galaxies. So I suspect you might be interested in grabbing those from us and kind of plugging underneath. So first question, are you ready for, or will you be once we generate it in 2022 or so, 40 billion kind of rows? And then the second question is, what should we be doing to prepare for it? So should we just give you the data? Should we work together on some sort of APIs? Or what's the best way? Will you be getting data in real time from us?
Well, I think the first question is, what do people really want to do with this data? So I mentioned to you before, we interacted a bunch with astronomers who have a lot of data. One of the issues that they had was, they've got all this data, but nobody's really using the data in a helpful way. And they say, gosh, if we could just have something like Wolfram Alpha type queries where people could just say, find me all the galaxies that have this characteristic and that characteristic and so on, and do that in natural language, then one feature of Wolfram Alpha is it has no documentation, okay? Because it needs no documentation, because it's supposed to just do whatever the person thinks they should type in.
Or we just watch your demo.
What's that?
Or we should just watch your demo.
Yeah, right. No, but I think I think the real issue is, what questions do people want to ask from the data? And there are things like, how will people refer to, let's say they want, for example, you'll want linguistics. I think we happen to already have these for like galaxy types. Like, is it a barred spiral? What people will say, I want to find barred spirals that have this characteristic and that characteristic. Or I want to find, places where there's a coincidence in time between a light curve that looks like this and a that. Right? The question is, how do they specify those kinds of things? Is there a reasonable language for them to specify those kinds of things? So examples, I think a big effort is in trying to get some idea of what kinds of questions people would ask, then try and figure out how will you specify those things. Now, for us, there's kind of two levels of specification. One is in the sort of precise symbolic language that we've developed in the Wolfram language. The other is in pure natural language. One of the things that's been really interesting to me, okay, so I'll tell you a little sort of background story. So in developing Mathematica over the course of many years, put lots of effort into maintaining this very precise, very formal, very structured language in Mathematica, okay? Where everything had to make sense, everything had to be consistent, everything had to be coherent. Okay, that was sort of design methodology number one. Then I started working on Wolfram Alpha. And the idea of Wolfram Alpha was just accept arbitrary, unwashed natural language input. And so you might think, can we make that nice and precise and consistent? And for example, some people at my company who'd been working on, Mathematica design, started them working on Wolfram Alpha, and it was like, this is crazy. This is, there's no way to make this consistent. Natural language is just completely inconsistent. So I decided, let's adopt a completely opposite design principle and just say everything is a heuristic. There's no consistency at all. It just does what people expect it to do. Okay. So I didn't know whether these would ever merge into anything. But what's been really interesting is being able to combine those two approaches. So for example, if you had to, you're typing in the name of a city, or the name of a star for that matter, if you had to go look in a manual to find out, how do I type Tor Ceti into this language, it's just a big pain, you probably wouldn't do it. But so what's turned out is, for example, entering things like names of entities, kinds of little lumps of kind of real-world computation. It's really convenient to be able to use natural language to do that. When you're dealing with more sort of structured algorithmic things, it's really convenient to have a precise symbolic language to do that in. So the merger of those two things has been pretty interesting. And I would say for astronomy, one of the interesting questions would be, what should the language design for astronomy be like? There's probably a combination of sort of natural language things where, the types of galaxies, for example, that's probably, you'll want some precise entities that represent those, but you'll also want, I don't know what they're, SB or B, I don't know what the acronyms are for types of galaxies, but you'll want all of those different, you might say, well, let's make a decision. Are we going to use so-and-so's nomenclature for galaxies or so-and-so's nomenclature? The answer is, don't make that decision. You're just going to provide linguistics that will support both of those and map them into some canonical layer that just represents them in a standard way. And similarly, when it comes to, I don't know, a description of, so I would say the first question is, how would you represent the queries? How would you represent, and I think the right answer is probably a combination of natural language and some essentially astronomy-specific primitives. Right. So for example, a very simple thing that we're doing, we have this geographics mechanism, we have geopositions and so on. In the next version of the Wolfram language, we will also have astroposition and astrographics and so on, which are just dealing with the coordinate systems for astronomy and such like. That's a place where you can kind of have a symbolic language extension that's useful for astronomy, and there are probably other ones of those. So that would be my first thing is, how do you represent the queries? Another thing is, what happens inside in the plumbing inside to deal with those queries. I would say, well, by 2022, you said, we should be ready for that kind of data by 2022.
Sounds good.
That's a while.
All right, thank you very much. So we are running out of time. If there's any last-minute question, very quick, then let's take it.
So I like this idea of natural language query. What I would like to see is an augmented form of, have a little tablet saying, I'm looking for, if I'm an astronomer, I'm looking for objects which have this kind of spectrum, and give me a pen that I can draw the kind of spectrum, or I'm looking for things that have this kind of shape. So natural language, and so much of the stuff is graphical in our environment. I don't even know the name for it. So I can't use the natural language, but I can say, it looks like this.
Right. Well, that's why it's really nice that our language supports things like images as kind of, I think that, well, for example, if you take that image identify case, there the input is an image. The output happens to be something that is an entity. So I would fully expect that in the case of, in the astronomy case, I would be shocked if it was not, it would be straightforward in our language to say, okay, I've got, 5 galaxies that look like this, and I want to find the closest, the galaxies that look closest to this by some measure of image distance. We have a bunch of measures of image distance that happen to be built into the language. The actual implementation of that across 100 billion galaxies, that's a bunch of computers to implement that. But I would say that that's exactly the type of query one should be able to do. Well, here, look, we can do, let's try something here. Let's see, I think we had an example. Let's try. How about let's just try one kind of example here. I think there's a simple classifier here, maybe. Yeah, here's a really, really trivial classifier that's probably not going to do a very good job for digits, okay? So there's a digit classifier. That'll train the classifier there just with that very, very tiny training set. Now, for example, I can go here. I can say, make a new graphic. Okay. Let's just, okay, let's draw, I don't know, let's try drawing ag. Okay, there's an 8, more or less. Okay, now let's see what happens if I take the classifier on line 131 and I apply it to my 8 here, and I bet it's going to give, wrong thing, sorry. Oh, it was called digit, so that's easy. digit, and let's take this thing here. Well, it's here. Let's just apply it to the thing that was on line 132, which was that 8, and it says it's a 4. Sorry. It's a small training set, but what's that? Yes, right. But you get the idea. I mean, we were able to just draw something here, and if I'd been, I could perfectly well have drawn something there and interpolated the function and then compared that with what, what I want to get and so on. I mean, this is actually something, it'll be coming to Wolfram Alpha, I hope, fairly soon. We have all kinds of input. So in Wolfram Alpha, you can not only just give textual input, you can also, for example, upload a picture to be used as part of the input. And uploading a drawn thing is something that happens to be coming soon for Wolfram Alpha. The challenge there, so natural diagram understanding is a different problem from natural language understanding. We happen to have been working on natural diagram understanding. There are two different cases. One is pure free-form drawn diagrams. The other is diagrams drawn with a tool that has lines and circles and so on in it. It's coming. That type of thing is standard natural diagram understanding is something that we've managed to make decent progress on, albeit the cases we first concentrated on are kind of trivial ones for geometry education and things like that. Okay.